In this project, we'll be generating paintings using deep convolutional generative adversarial network. So in this project, we learn and understand about image generation, we learn about GANs, and finally we'll deploy our model as a Flask web app. So what is image generation? Image synthesis or generation is the process of creating new images from some form of image description. The kinds of images that are typically synthesized include test patterns, scenes with simple two-dimensional geometric shapes, image noise, images containing random pixel values usually generated from specific parameterized distributions, computer graphics, scenes or images based on geometric shape descriptions. Often the models are three-dimensional but may also be two-dimensional. Shown on the left are images generated by a model called DCGAN. This model was developed by NVIDIA. All four images here are fake images which are completely synthesized from noise using the DCGAN model. In this project, we'll look at a specific model of GANs known as the Deep Convolutional Generative Adversarial Networks, or DCGAN. They are a great starting point for image synthesis. In the coming slides, we see the working of DCGANs in detail and then proceed with implementing such a model. The dataset is a set of paintings which we will use to train our model and try to mimic images from. So let us see what are GANs and what are DCGANs. In a GAN, there are two neural networks competing against each other. A generator which creates fake data and a discriminator which tries to distinguish between fake and real data. The two networks are constantly learning from each other, and the goal is for the generator to create data that the discriminator can't tell is fake. This allows GANs to generate data that is realistic and difficult to distinguish from real data. On the right hand side, we see a block diagram of the architecture of the generative adversarial network. We can see that there are two blocks, one is the generator and one is the discriminator. The generator is getting a latent space and is also getting a summation of the noise that is being given into the generator to generate fake images. Those fake images are then appended to real samples and then put into the discriminator to classify it into fake or real. Accordingly, whatever error we are getting from the discriminator is then used to fine-tune our generator to learn the weights and generate better fake samples. Similarly, in a deep convolutional GAN or a DCGAN, the concept is kept the same, that is having a generator and a discriminator working and learning from each other. Only this time, the actual models are made up of convolutional layers to deal with images or 2D/3D space. The generator model has multiple upscaling convolutional layers providing the final image shape desired, while the discriminator has the normal convolutional layers to reduce the dimensions and the weight. On the right hand side, you can see the generator network structure, where from a latent space of 100, we are reshaping it into an output 3D volume of 4x4x1024 and using upscaling convolutional 2D layers to get our final image size. On the bottom half of the image, we can see a discriminator network, which is a general CNN network used for binary classification. We can see that the image input in this network is the same as our output of our generator network. Now that we have a certain idea about how DCGANs are made, let us investigate an implementation of the model using TensorFlow and Keras. Since this kind of task is very GPU intensive, it is always recommended to train on a cloud GPU if we don't have one. Even then, it takes up a lot of computational hours, so we shall train for only a small time frame and see the results. So firstly, we're going to import some important libraries and modules that will help us to read the data and create the model. Next, we are setting a random seed so that we can recreate the output. We are setting the noise dimension to be 100, which is also the latent dimension or the random vector. We are setting the batch size to 16 and the steps per epoch to 4000. This is open to experimentation and you can play around with it to get the best output. We are also setting the epoch number to 10. After that, we can see here that we are setting the dimension of the image to be 128 cross 128 cross 3. That means it will be a 128 cross 128 size image with RGB values, not grayscale. Next, we are setting the optimizer as an Atom optimizer available in the Atom v2 class. We are setting a custom learning rate of 0.0002. All right. Now we are defining the path where our dataset exists. Using CV2, we'll be reading the images in our path. So here we create an empty list and we use os.listdir to go through our path and one by one read the images using cv2.imread. Once the image is read, we convert the image from the BGR format to RGB format and then we resize the image to our desired shape of 128 cross 128. Finally, we append the image to our data list. After reading all the images, we can see that we have around 4,117 images in our dataset. After we read all these images, we are changing the list type to a NumPy array and we are normalizing the pixel values from a range of 0 to 255 to a range of -1 to 1. Finally, we are reshaping our NumPy array in a single 1D vector. Alright, so after we have done the pre-processing, we can proceed with creating our generator and discriminator models. So we can see here, we are importing initializers and layers that will be required to create our generator model. Here you can see we are importing the dense layer, the conv2D, the conv2D transpose, and the reshape layer. We are also going to use the leaky ReLU activation instead of the ReLU activation. And we are importing the sequential model class since our model will be an instance of the sequential class. So let's create a function, create generator CGAN. In this function, we'll be creating the generator model and returning it. So let's take an instance of the class sequential class. We are setting D as 4. This will be our starting dimension of the image. We add a normal dense layer with the dimensions 4 into 4 into 256 and we set the input dimension to be 100, which is the latent space dimension. The activation used is leaky ReLU. Then we reshape this into a 3D volume which is of size 4 cross 4 cross 256. After that we can proceed with adding our upscaling convolutional layers. So here you can see that we are adding our first upscaling convolutional layer which is called conv2D transpose. Each upscaling will increase the dimension by 2. So here after this block of upscaling, the dimensions of the image will be 8 cross 8. Then we again put an upscaling block here with 128 kernel filters. After this, the dimension will be 16 cross 16. After this block, the dimensions will be 32 cross 32. After this block, the dimensions will be 64 cross 64. And finally, the dimensions after this block will be 128 cross 128. Each convolutional 2D transpose layer is using 128 kernels of size 4 cross 4 and the strides as 2. Finally, we add a normal convolutional layer with the channel size as the kernel filters, 3 cross 3 to be the size of the filter and padding being same. Make sure that the activation is tan-edge and not sigmoid since we have normalized the pixel values to be in the range of -1 to 1. Finally, we compile the generator model using the binary cross entropy loss and the optimizer Atom that we set initially. Let us return this generator. Next, we can proceed with creating our discriminator model, which is a general CNN model. Here we can see that we have created a function called create discriminator CGAN. Again, the discriminator model will be an instance of the sequential class. Then we add a convolutional 2D layer with 64 filters of each of size 3 cross 3. The input shape here is defined as 128 cross 128 cross 3. We add total of 4 convolutional layers with increasing filter numbers, but all of the filters are the same size. Finally, we flatten the output volume to a 1D array and then insert a dropout layer so that 40% of the lowest performing neurons will be rejected. After that, we attach an output layer having one neuron and an activation of sigmoid since it is a binary classification problem. Finally, after making the model, we compile the model with binary cross entropy loss and the optimizer as the same optimizer Adam. We return this discriminator. Now that we have created the discriminator and the generator models, let us call that and use that to create our GANs model, which is the connected model. So here we are using the keras.models.model class. We are calling the create discriminator CGAN and create generator CGAN functions to get our discriminator and generator models. We are setting the discriminator to be non-trainable. Next, we are creating a new input layer, which will be the input layer to the GANs model. This input layer will have the shape defined by the noise dimension or the latent space dimension. Finally, we are creating a pipeline to make a connected path that input layer is fed into the generator using this, and then the output of the generator is fed into the discriminator to get the final output here. So these three lines here make the pipeline of the entire model. So finally, we can put this input point and this output point into our model function to create our GANs model. After that, we compile that model with binary cross entropy loss and optimizer Adam. Next, we create a function to show or plot the images after each epoch. So here in this function show images, we are passing the parameters noise and size figure. The noise is what will be used to generate the images from the generator, and the size figure is used to show the figure or plot it. So here we can see using the noise, we use generator.predict and we pass the noise here to get the generated image. After that, we create a figure. After that, we iterate through the generated images and plot it using subplot. To make sure that we see the images properly, when we are plotting it, we'll be reshaping the images into our desired size, which is 128 cross 128 cross 3. All right. So coming to the training part, for epoch in range epoch, so that it goes through each epoch, and for batch in range steps per epoch. So in each epoch, there'll be 4,000 steps to train, and in each step, there'll be 16 images that are taken in one go to train the model. We are creating a normal distribution for our noise with the size as batch size 16 and noise dimension 100. So that means 16 images of each of size 100. We are sending this noise to generator.predict to create fake images. Next, we are taking the real images as random from our data set and then concatenating the real images and the fake images to create one data input for our discriminator. After that, we are creating a NumPy array of size 2 into batch size because there are 16 real images and 16 fake images. We are setting the values of the array, the first 16 values of the array to be 0.9 and the last 16 values of the array to be 0, denoting that the first 16 images are real and the last 16 images are fake. Next, we send our images and our output array, which is disk y, to our discriminator.trainOnBatch and get the loss. After getting the loss, we create a NumPy array of ones of size 16 for our generator, and then we send the noise and this array to our GANs model to get our generator loss. In this way, the generator will be trained according to the discriminator outputs. After one epoch has been trained, we use a different noise sample and send that noise to show images to generate our output images. So after each epoch, we can see that the model is generating 25 images. And after each epoch's training, we can see how slowly the model is capturing the details and the way the paintings are made. Obviously, because we are training for such a less time, it's not very realistic and very accurate, but we can understand and see that the model has been able to capture the characteristics and the general shape of the images and of the portraits. So after training for 10 epochs, we are going to save the GANs model and our generator model, which we'll use for generating the images. Finally, we create a pipeline that we can use in our Flask web app to get the final generated image. Here we can see that we are generating a noise. The size is of 1 cross 100. That means that it will generate only one image. We are sending this noise to our generator.predict and then finally plotting it. So now that we have seen how to create our model and save it, let us see how we can create a Flask web app. So to create a Flask web app, it is necessary to have a certain structure of the directories. So let us see that. So in our directory, we can see the static folder. This folder stores all the input and output images that we'll be using in the Flask web app. The templates folder here deals with the index.html file. It stores the index.html file. Let us open that. Alright, you can see that the index.html file is a very small app. The main part here being the click button to generate, which is a form type. It has no input, but it has a submit button which we can click to generate new images. And the second important part is the image tag here to show the actual saved generated image. Next, we have the app.py and the model.py in the root directory and the generator.h5 model that we saved in our Jupyter notebook. So let us look at app.py. In app.py, we are importing the Flask class, the render template function, and the request function. We are also importing some important libraries to help with storing, reading, and generating our model. Also, from the model.py script, we are importing the generate function. So here you can see in the model.py script, we have the function generate. So we import the generate function from the model.py script so that we can call it in app.py. So we create a new instance of the Flask class known as app. We set the upload folder to the static folder using this line here. We put the allowed extensions at PNG and JPG so that only PNG and JPG images can be input in our HTML file. Finally, we configure the app to default our upload folder to this particular directory that we have defined. Next, we are defining the image row, image column, and channel. That means we are defining the image dimensions, which is 128 cross 128 cross 3. Now we are configuring the app to call the function home when the web page is reloaded. This function home will return the index.html file using the render template function. So this function basically deals with reloading and rendering our HTML file whenever we call it. Next, we are configuring the app to call the function upload file whenever the method get or post is used. So in the upload file function, we can see that if the request.method is equal to post, that means in the index.html file, when the submit button has been pressed, using this method post, that information is communicated to the app.py script. When we get that information, we are creating a path, which is our static folder and the name of the file that we will store to show in our web app. We are using this line here so that matplotlib doesn't open new windows when we are plotting the image. If matplotlib opens new windows, it will kill our app. Next, we are calling the generate function to get our output image. So let's see what the generate function does. In model.py, we can see that we have imported a few libraries to help with reading the model and generating the image. We have set the base directory of the app. And we have used keras.models.load model to load the generator model. Setting the noise dimension as 100 or the lattice space as 100, we then define a generate function here. In that function, we are creating a noise of size 1 cross 100. That means that only one image will be generated. Using that noise, we are sending it to generator.predict to get a generated image. After getting the generated image, we are denormalizing it to have pixel values from 0 to 255 using this line here. And then we are sending that image back to our app.py script. So here that image is stored in this variable here. We are reshaping that image to a desired size, which is 128 cross 128 cross 3. And then we are increasing the image size to 512 cross 512 using interpolation. Finally, we are plotting that image and saving it at the desired path. After saving that, we are again calling the render template function to render our HTML file with the new image stored in the static directory to show in our web app. So here you can see the image tag has the source static/input.png. That means whenever the HTML file is rendered, it will show the input.png image in the static folder. Finally, to run the app, we use this code snippet. So let us run this app. Okay, so let's copy this link. So let's forget about this image right now because this is from a previous testing. We'll click submit to generate a new art. So here you can see that has generated an image. You can see the basic characteristics that it has acquired or learned after only 10 epochs. Of course, if we train it for a large number of epochs, it will approach realism.